this example, the ultimate cooling is provided by a liquid cold plate along the base of the chassis, which runs fluid at 55 degrees C. The electronics board is generating 50 watts concentrated near its center and has additional components totaling 50 watts distributed across the board. To successfully reject the waste heat to the liquid-cooled base, the heat must conduct from the components to the conduction card frame edge, through the mechanical retainer or wedge lock, and down the card guides to the liquid base. In the baseline example, we are assuming all components are aluminum, and the wedge lock is an off-the-shelf design. As we analyze the base model, you'll notice significant temperature rise from the cold plate to the max card temperature. The total delta T is 69 degrees C. In most cases, that delta T is not suitable for successful operation. Therefore, designers must find a way to reduce the thermal resistance. The largest delta T in the system is from the centralized component to the card edge, which means the design is limited by the thermal conductivity of aluminum. By strategically embedding heat pipes, you can greatly enhance the bulk thermal conductivity of the heat spreader. The resultant embedded heat pipe card frame is known as a high thermal conductivity or high K plate. After reinserting a high K frame in place of the aluminum conduction card frame, the max temperature of the card drops from 124 degrees C to 96 degrees C. High K plates in 6U form factors can routinely achieve thermal conductivities of 600 to 800 watts per meter Kelvin, dependent on component placement. The next area for thermal enhancement is at the frame to chassis interface. Off-the-shelf wedge locks provide mechanical attachment, but are not efficient heat transfer devices. Due to limited surface area and poor thermal path through metal-to-metal interfaces, the overall delta T is pretty significant for a short conduction path. ACT's Ice Lock was designed to address both challenges. The design expands in all directions, contacting an additional surface on both the board frame and chassis. This provides more surface area while also bypassing metal-to-metal interfaces as the primary thermal path. By changing from an off-the-shelf wedge lock to the thermally superior Ice Lock, the designer continues to reduce the overall delta T of the system. The card max temperature is now 92 degrees C, which is a total delta T of 37 degrees C. With these two minor changes, neither of which significantly affects geometry or weight, the system operates over 30 degrees cooler than the baseline model. The final area affecting overall delta T is the conduction through the card guide or chassis. Each sidewall must conduct heat from the card interface to the liquid-cooled base. Again, the baseline is aluminum with a thermal conductivity of 167 watts per meter Kelvin. To reduce the gradient, we convert the chassis to a high K sidewall by embedding heat pipes. This final change drops the overall delta T by an additional 13 degrees C. The max card temperature is now 79 degrees C, which is a safe operating temperature for most electronics. From the baseline to the fully thermally enhanced model, the thermal savings was 45 degrees C. This type of savings can allow for higher power densities or added margin to the system. Thanks for joining us for this example of how ACT's Ice Lock wedge locks can improve thermal performance. For more technical information about Ice Lock, as well as access to an installation guide, visit our website at one-act.com.